Oh, I should wear the mic.
Yeah. Put in your sock, in your pocket, and then there's a little clip here.
Oh, I see.
So now we'll have our second lecture series started. Previously anticipated, Remi will deliver the entirety of it. And so, well, the title is a differential approach to Ax-Schaunel theorems.
Yes. So thank you for the invitation. It's a pleasure to be here. So the lecture have been prepared under the guidance of Guy, so I hope they will be nice. And they are all based on a paper of David Blasquez-Sang, Guy Casal, James Freitag, and Ronnie Naglou, which is called a differential algebraic approach to the Ax-Schaunel. So the goal of this lecture, the general goal, will be to describe some techniques from differential Galois theory. To prove some transcendence results about certain analytic functions satisfying certain systems of PDEs, certain systems of algebraic partial differential equation. Okay, so I'd like to be a little bit more precise before starting the content of the first talk, and to say that, so for differential Galois theory, there are various variants of that, and we will use two variants. I would like to present in this lecture two variants of that. The first one is the classical Picard-Vessieux theory. So every time I have to write Picard-Vessieux, I will write PV, which is about systems of linear equation, y prime is equal to a of xy, and whose setting is differential algebra in characteristic 0. And the second variant of this that I will present, which will be the thing where we'll spend the most time on in the next lecture using, is a Galois theory for principal connections on principal bundle. Okay, and this is something you can find in some text of Malgrange about non-linear differential Galois theory, but he first explained the linear version in this setting. There's also an article of Blasquez-Sang Casal, which is called, I think, Parallelism and Lie connection, and the paper I was just mentioning of Blasquez-Sang, Casal, Freitag, and Naglou. Okay, so my first goal on my first lecture will be to present these two versions. And so what kind of transcendence result we are aiming for? The right model for the transcendence result we are aiming for is the following theorem of Ax, which I will call Ax-Schaunel for the exponential function. This is the result of Ax in 71, which says the following thing, that if you take, how do I get the variable z or x? Yeah. Z, if you take R power series, which are non-constant, and you compute the transcendence degree of this R power series and their exponential, okay, and you compute this transcendence degree over C. if it is smaller than what you expect, so if it is smaller than r plus 1, then something very particular happens. Then there exists E1, ER in Z, so that's what you make the sum of the Fi with this coefficient in Z, you end up in C. Okay. And so the goal will be to prove this kind of theorems, but for other type of functions, so that's the J function. Okay. And so there's a corollary of this. We will see that it's optimal by the corollary, for example, which is, so this is Ax-Schaunel for the exponential, but which will be Ax-Lindemann. So for X, so I'm only talking about a, yes?
Basic question. So very like, what did you expect?
Why
did you expect that R plus 1?
So I'm going to explain it. In the corollary, it will be clear why this is optimal. Is that what happens if you take F1, Fz, be all rational function. Okay, they are not only power series, they are rational function. So now when you compute the transcendence degree of these functions and their exponential, you see that this is the same thing as computing the transcendence degree of the field C of Z and their exponential. Okay, because all these functions are rational, they are all in C of Z, so they are, you get exactly this field, but this field has maximal, so you have R plus 1 element, so it has at most transcendence degree R plus 1. Okay, so you see that when you take all the power series to be actually rational function, you see that this transcendence degree here is at most R plus 1. So when it's R plus 1, you cannot say anything. Okay, so if this is strictly less than R plus 1, which is exactly the number of generators of this field over C, okay, then there exists E1 ER in Z such that E1 F1 of Z plus ER FR of Z is in C. Yes?
For example, if it's smaller than R minus 1, to have several vectors of relation.
So we will see, I think so. It's about describing, so we'll see how, so I will explain, at least in that case, I think this is true. And so the first thing I would like to do is to present these two Galois theory and use the old one, the classical one, to prove this theorem. Okay, just the corollary, not the theorem. Then we will see how to use the more advanced version of principal bundle, principal connection, and principal bundles to prove this kind of theorems. Okay, so the better version, but not for X, but for other types of functions. Okay. Does that make sense? Yeah, any questions? Fy of 0 is 0, not necessarily. Okay, here, if I want to apply it to rational function, for example, I will take a point which is not a pole of all these rational functions. So you can apply it to any point. Okay, any point in C.
Can you say with these bounds when these functions are rational or zero?
So can I say?
Can you say something like if this F plus 1, then they're rational functions or something?
No, so for example, you can take F1 to be the log of a rational function, and the other one to be rational function, and then the exponential of the log of the rational function will be the rational function. Okay, so I don't know anything which says when it's exactly R plus 1. The goal here is to describe what happens when it's less than what is expected for rational functions. So the classical Picard-Vecious theory. So I will have to give you a couple of definitions of differential algebra. Yes, complex numbers, but I mean, I think many things are valid about this assumption. No. So I will first give you, so this, yeah, at least this theorem is valid in for all field of character, for all algebraically closed field of characteristic zero. So a differential, so I will start by giving you some definitions of differential algebra in characteristic zero. So all my rings are of characteristic zero. So what is a differential ring? Is a pair R delta, where R is a ring, and delta is a derivation. Okay, so delta goes from R to R and is a derivation. What does that mean? It means that if you take, it's additive, and it satisfies Leibniz rule. Okay, so every rings are commutative, right? So we don't care in which order we write it. Okay, so a differential ideal of a differential ring is an ideal of a differential ring R delta is an ideal. Yeah, R is commutative. Okay, all rings are commutative and on characteristic zero. Okay. So it's an ideal R included in R such that it's stable under the derivation. Okay, and I just need a third definition, is that a differential field is a differential ring whose underlying ring is a field. Okay. So I will just use these three notions. Hopefully. Okay, I will give you a bit of geometric interpretation of this when I will present the case of principal bundle. But so the setup for the classical case is the following. Okay, so you have a field, if you fix K delta, a differential field. Okay, so you can think about the field of rational function and though with the usual derivation. Okay, the field of meromorphic function on an opposite U and though with the derivation, same derivation, or the field of Laurent series at X and those with the usual derivation. These are all okay, natural example. And you're given y prime is equal, so let me write 8 times y. Okay, a vector valued linear differential equation. So y is y1, yn. Okay, this is what you're trying to, this is the unknown. Y prime is just you take the derivative coordinate by coordinate, and A is a given matrix in your field case. And the goal is to define the Galois group of such an equation. Okay. P is it's mat P, so the square matrices of size P times P. Oh, yeah, P is equal to N. Okay. Okay, so how do you define the Galois group? You do like you do in the usual case of Galois theory. You start by trying to find a field extension. Here, a differential is field extension that contains all the solutions. So all the solution, what does that mean for a differential equation? It means that, so you fix, so in the setup, a fundamental matrix of solution. So let me fix, so you have your differential field, and we are fixing a differential ring extended this differential field. Okay, you have this differential field, and you're not looking for solution in K. Okay, you're looking in solution in something bigger. So a fundamental matrix of solution is a matrix F in GLP of R. So it's an invertible matrix, okay, such that the columns of F are solution of your equation. We'll give a name to this equation. Okay, so the way to write that the column of F have solutions of S, you can just use matrix notation. And why? This means that if you take F prime, so here this is the matrix where you differentiate coefficient by coefficient, this is equal to A times F. So you see, we had a vector valued equation, and we're looking for a matrix solution which is invertible. This will be the same thing for principal connection. We will move from vector bundles to principal bundles. Here, this is the move from vector bundle to principal bundle. So this is what I'm going to do. So for a fundamental matrix of solution, there's no requirement, but for when I will define a PV ring, I will ask exactly what you say. So now that I've defined that, I can define a PV ring. I will take another definition, the one you have in mind. For S is a differential ring R delta, extending K delta, such that, so this is the analog of a field of decomposition for a polynomial in the normal case, such that two things happen. The first thing is that R contains a fundamental matrix of solution. F, so there exists the thing I just explained, and is generated by the entries of R, of F, by the coefficient, and the inverse of the determinant of this matrix. Okay. And there's a second condition, which is so this is the easy condition, but the right condition to find, so which is equivalent to the one that was just mentioned to me, is that, so let me call that A, and B is that R is a delta simple ring. What does that mean? It says it has no non-trivial differential ideal. And so remark is that B implies that R is an integral domain. Okay, if you have a maximum, okay, I will just this condition to be a delta simple ring, it implies that you're an integral domain. It's not very hard, it's just a computation of differential algebra. I will go back to something a bit nicer after. And frat R, the field of function, L, is called a PV extension of S. I require both condition A and B, but B alone, I think you might assume that R is finitely generated. It implies that it's an integral domain. Okay, we'll come back to that. Essentially, this is the same thing as saying that the maximal differential ideal is always prime, but it's not always maximal ideal. Okay. So what is the main result? The main result is existence and uniqueness of such things. And so this is the following proposition. That first, PV rings always exist. So for every linear system, I can find a PV ring and two PV rings associated to the same system. Are isomorphic. Okay, but they are not canonically isomorphic. And so the Galois group will be exactly what measures how not canonically isomorphic are the PV ring of an equation. Okay, I want to give a proof of I, and I want to give two proofs. Okay, which are not complicated proofs, but because they will show up again, you will make the connection with the case of principal bundle we will show after. And so the thing I want, the observation, which is pure differential algebra, is that if you take a ring R, R a ring satisfying A, the following are equivalent. So which is generated by a fundamental matrix of solution of a linear differential equation. So the following are equivalent. R is delta simple, saying that the ring R has no differential ideals is the same thing as saying that the set of functions in the fraction field of this ring such that the derivation is equal to 0 is equal to C. Okay. And so you see, this is telling you that you don't have rational integrals. This is telling you that you don't have delta invariance of variety. And for these specific rings which are of this form, these two are equivalent. Okay, and this is pure differential algebra. And so how do you use this to produce Picard-Vessier ring? What you do is that you take your system of this form, okay, and A of X, let's say that it's a matrix in C of X, matrix of rational function. So you look in C, you get rid of all the poles of A of X. This is the set of poles of A of X. We see, oh, okay. So I'm assuming that the field of function of K is C. I'm assuming you're right. I forgot to say it. The differential field, you see the three examples that I gave, the field of function is equal to C, the field of constants of K. Okay, so I'm assuming here, I take a differential field here, field of constants C. Okay, so this is how C relates to K. Okay, so, and what you do is that you take a simply connected open set, which doesn't mean the poles of your function, and then the fundamental existence theorems for solutions of linear differential equation tells you that you can find F, which is an inverted, a fundamental matrix of solution in M of U. Meaning, actually, which are made of holomorphic function in U. Okay, if you have a linear differential equation, you take a simply connected subset of the complex plane which doesn't meet the poles, you can find a global matrix of solution. And then you just look at, in M of U, you just look at K, you just look at C of X, where your joint F and 1 over det of F is a PV ring. And so you see, by definition, it satisfies A. And why does it satisfy B? Because it satisfies that the field of constant of this, of the fraction field of this, is a subfield of the field of constant of the meromorphic function, so it's C. Okay, so if you take solutions on a simply connected open set of linear differential equation, you will generate a Picard-Vessier equation, a Picard-Vessier ring.
So what's the relation now of C of X and K?
C of X is K. So I'm just giving the proof for C of X is equal to K here. Okay. But now here is a purely algebraic. So, but I'm just saying that there's these two versions. And now here is a purely algebraic proof of the existence of Picard-Vessier extension is that you look at K, you set R0 to be K with 3 variable Xij, and you localize at 1 over det of Xij. Okay, Xij are 3 variables. You look at this ring, which is generated by these 3 variables. Okay, and you set the derivation delta 0 by delta 0 of Xij is equal to AX ij. Okay, you just abstractly define a ring which contains a solution of your, which contains a fundamental matrix of solutions of your differential equation. Okay, but this is not a Picard-Vessier ring because it's not delta simple. So what are you going to do is just you take M to be a maximal delta ideal, and you take the quotient. Set R0, which is R divided by M. Okay, this construction is the one we will use for principal bundle of connection. Okay, and it makes the connection between the two theories. Does that make sense? Should I put it a bit higher? Does that make sense? So you take this ring with this derivation and you mod out by a maximal differential ideal. So you have a choice here. Okay, but the second point tells you that first these two rings are isomorphic, although they are constructed differently. And whichever maximal ideal you pick, you will get the same ring. I mean, we get isomorphic ring. Okay. So now what is the Galois group? The Galois group, okay, let me observe. Essentially, the Galois group is the automorphism group of a Picard of a PV ring. So let S be a system as above. Okay, and you consider R a PV ring associated S and Y a fundamental matrix of solutions. And so the first, and so essentially we are looking at the group. So let G be the group of differential automorphism of U ring R fixing K. So this is group of delta automorphism of R fixing K point 1. Okay. So the observation is that if you take sigma in this ring. And you compute the image of the fundamental matrix of solution. Remember that they generate R. Okay, this is again a fundamental matrix of solution of the same system. This is because this is a delta automorphism. So it sends solution of a differential equation to solution of the differential equation. And since it's invertible, it sends an invertible matrix to an invertible matrix. So sigma of y is equal to y times a matrix C sigma, where C sigma is in GLP of C. Okay, so if you compute sigma of your fundamental system of solution, you get another fundamental system of solution. So you get the fundamental system of solution you started with times the matrix. Okay, and so the observation 2 is that if you look at the morphism from sigma to sense to C sigma, which goes from this differential from G to GLP of C. Okay, this is injective. And the image is an algebraic group. Is a closed algebraic subgroup. Okay. Okay, and now the observation 3. That you see, I've made a couple of choices. I've picked a Picard vector ring and the matrix Y. So if R prime Y prime is another choice. Okay, the image is replaced by a conjugate in GLP of C. Okay, so it's often like, so the matrix, the Galois group of S over C of X is the image, the isomorphic image of O delta of R over K. Okay, and it's only well defined up to conjugation. Okay. That it's an algebraic subgroup. Okay, so if you think about this presentation here, okay, GLN of C acts on this ring, okay, by sending Xij to Xij times C. And this algebraic group is exactly the group that preserves your maximal ideal. But preserving a maximal ideal is an algebraic condition. Okay, and it's injective just because a fundamental matrix of solution generates R with its inverse of the determinant. So if you give the image of the fundamental matrix of solution, you fix K, so you've given everything. And so the key point is that we have a Galois correspondence. Yeah. No, I didn't prove that. Okay, I stated it. It's not that easy to prove. Okay, but it's we haven't proved it. We'll see. Yeah.
Because the question: why do we define it as to be the image, not just the whole orbit of the conjugation?
So this is, I mean, this is a way of speaking to say that actually this is the whole orbit, which is but I mean, I will often talk as a group. Okay, but this group, as a pure algebraic group, it's well defined. And as a subgroup of GLN of C, you can always conjugate it. I mean, you cannot distinguish it from a conjugation.
Yeah, but thinking about the orbit, would it be easier to think about the whole family of all of them at once?
Yes, I mean, so there's another way of doing it with groupoids that also solve this problem of having something that is only defined up to conjugation. But I mean, this is so we will only make statements up to conjugate, up to isomorphism. We'll always say the Galois group is isomorphic to a subgroup or things like that, which I mean, we will use that this is only well defined up to conjugation. Okay. So let me take about the Galois correspondence. Okay, and the Galois correspondence would be a machine that transforms questions about finding algebraic relations to questions about subgroups of algebraic groups. Okay, so you take S, a system as above. So in the setup, consider R PV ring, and K is equal to frac R. L is equal to frac R. Okay, so there is a one-to-one correspondence between so closed algebraic subgroup of the Galois group of S of K, and differential fields extension K in L. So let me write it in here. So which are in between L and K. Okay, more there. So M over K is normal is a PV extension if and only if the corresponding subgroup is normal. Okay. Okay, so to use this, so now I want to use this to prove this Ax-Lindemann theorem I told you about. Okay, and to use this, I will need to get a lemma about algebraic subgroups. Okay, and so I will make an assumption. So I will give a definition. So an algebraic group. Yes. 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 So where is R here?
R was used to build.
Yes.
So let's say it's on L.
Yes.
Then you have a field which is in between.
Yes.
What is R?
So L is frac R, right?
Yeah. Right.
And so it means that we work generically on the base, right? If we think about a vector bundle on the base, you have the curve and the vector bundle here, okay, and the linear equation which goes like that. It means that instead of having, we will have things that we always allow to replace the base by a smaller subset. This is why the base is K, and somehow the subvariety we only know what they do. I mean, the thing is, we only know what they do on an open set, right? And so instead of, so it's harder to define, I mean, the differential algebra is very powerful to give the Galois correspondence. But geometrically, it's harder to picture exactly the Galois correspondence. And in the case with principal bundle and connection, we will not use the Galois correspondence. We'll have other tools. Okay, but in this setting, this is the main thing. And we will work, when we will work geometrically, we will use a different tool because, I mean, You can make sense of this, but it's harder to express. At least it's not done. This is not how they proceed in the paper, by proving the analog of that.
I'm not sure I understood the question of Carlo, but it occurred to me that perhaps this the Carvesius extension that are between would correspond to quotients of this flat connection that you have there.
Yes, something like that, but it's not, we don't say something about between R and K, right? But between the function field of R and K. So somehow it's quotients up to a rational map. It's more like a dominant, if you have your projective bundle, dominant map, but not that are defined everywhere. I guess it's something like that. Okay, but indeed, this is what will play the role in the other case, is quotient of the principal bundle by a subgroup. Okay, so let me give you a lemma that we will use in both cases, which is called Gursa-Colchin lemma about algebraic group. So an algebraic group is definably simple. So essentially, if it is simple, okay, G, if every normal subgroup, algebraic subgroup, G has dimension 0. Okay, so we weaken a little bit the notion usually used of simplicity. We allow normal subgroup, but of dimension 0. Okay, and it's not also simple. So examples, because we want all these examples to fit in. Okay, if you think about SL2, yes?
Can you just read out one is
So the correspondence? So to a subgroup, you associate the elements which are fixed by all elements of this subgroup. And to a differential field extension, you associate the element that fix. So if you take, so one thing is that O delta of R over K is isomorphic to O delta of L over K. Okay, because they are both generated by a fundamental matrix of solution, and they send a fundamental matrix and a fundamental matrix. So if you have a intermediate field extension, you can consider the set of sigma in the Galois group of S over K, of O delta L over K, such that sigma of X is equal to X for all X in M. This is the fixator, the element which fix your differential field extension. This gives you a subgroup. And if you take a subgroup, you can take the elements that are fixed by. M is in the middle of K and L, yes. So this is usually what people write in Galois theory, right? In classical, you make this kind of diagrams where you write inclusion with that. That's why, if you want, I can write K included in M, included in L, and this is a differential field. But usually you make diagrams with this. Okay. So we have weakened a little bit the notion of simple group to allow groups such that SL2, which has a finite quotient, okay, any simple group. Okay, but also GM, okay, and an elliptic curve, for example. Okay, all of this goes into these things. So what is Colchin-Gursa lemma saying? So it tells you the following thing. You take G1, Gn, Gr, are simple, are definably simple. Algebraic group. Okay, and it will describe the subgroup on H, a subgroup of the product which project, assuming that it's a proper subgroup, which projects on each factor. Okay, so what the lemma will describe is the subgroups of product of definably simple algebraic group which project on each factor. Okay, so the first thing, then one of the two following cases happen. And this is the common ingredients in both, I mean, in all proofs that we will use here.
When you say project projectively.
Yeah, project subjectively. One of the following cases occur. So the first thing that can occur is that there exists I different from J, such that Gi and Gj are non-commutative. And an isomorphism F from Gi mod out by the quotient to Gj mod out by the quotient, such that every time you take a point in your subgroup, okay, f of pi of xi is equal to pj of xj, where pi is the projection from gi to the quotient.
This is the center.
Z is the center. Yeah. Okay, so if you take simple groups that are really simple, okay, then, but we want to allow SL2, okay, then there is just exists an isomorphism such that G is included in the graph of this isomorphism. Does that make sense? Okay, essentially it tells you that the only way to produce between non-commutative groups, subgroups of the product, is to take two of them and to take an isomorphism between two of them and to take the inverse image. And the second thing that can happen is that there exists J of 1, J of L. So you can find indices such that the group that you have selected are all commutative. And surjections so f I from each of these groups to the last one. Okay, for I is equal to 1 to L, such that for all x1, xn in H, so if you make the product of the fi of xi for I, so the of fgi of xgi for I is equal to 1 to k to L, you get always a 1. So it's one Okay, it's 1 G. Okay, so the second thing that can happen is that you take G1, you can take now more than 2 of them, you have L of them, but they are all essentially isomorphic. I mean, so since they are all simple, the quotient here is a finite group. Okay, so you have essentially isomorphism between them, such that the group is included in the product of this isomorphism is equal to the identity. The statement makes sense?
So your algebraic groups are algebraic groups or linear algebraic groups?
They are algebraic groups.
So
Okay,
you
you
have a billion varieties in the.
yes, you can apply it to elliptic curves too. Okay, not in Picard, not the Picard-Vessios theory, but this lemma is a pure lemma about algebraic groups, and Goursa, it's even a pure lemma about groups. If you take simple, here I gave a version for algebraic groups which are definably simple. Okay, but if you take simple groups, this is a lemma about groups. So it's combinatorial lemma, but it's not something that has anything to do with algebraic groups. It's purely combinatorial. Okay, if you take 3 simple groups and you take a subgroup of these 3 simple groups that project on each factor, actually there is an isomorphism between 2 of them such that the group is included in the.
I think you already answered. H is a subgroup, algebraic.
Yeah, H is a proper algebraic subgroup.
The order is fixed, right? So you can, whatever the original order was, you can always choose trace increasing.
Yeah. Yes. Okay, so I will not have time to describe the principal connection case today, so I will do that next time. But I want to show you how to use that plus this to prove this Ax-Linderman statement for the exponential. Okay, and there are other exercises about doing the same thing for the logarithm or for the solution of the Airy equation. So I want just to describe a simple example. So you take f1 of x, fr of x, rational function, okay, which are not constant, and you assume that the transcendence degree of this field over C is less than r plus 1. And you want to show that there exists E1, ER in Z, such that E1 F1 of X plus ER FR of X. Yeah. So this is the exponential here. E to the power F1 of X, E to the power FR of X. Yeah, I don't put F1, FR, instead I put an X, okay, because they are all rational functions. That makes sense. This is a statement of Ax-Linderman for the exponential. Okay. So the sketch of the proof is the following. You do the following thing. You start by rewriting this by saying that, okay, this tells you that the transcendence degree of C of X and this exponential over C of X is less than equal to R. Okay, because the transcendence degree on the C is less than equal to R plus 1. Then if you look at the transcendence degree over C of X, this is less than equal, this is strictly less than R. Okay. And now you look at the exponential function. You say that C to the power X e to the power X is a PV extension of C to the power X corresponding to the simplest linear equation corresponding to y prime is equal to y. Okay, if you just take C of X and one exponential, Okay, the Galois group, is GL1 of C. This is GM. Is GM. Okay, so you compute the Galois group of the function you're interested in, which is the exponential. And then, so actually, there is an exercise in the exercise sheet about that. The fact that this is a Galois group with a Galois group C of x tells you that for all f of x, which is non-constant, actually, this is, when you pre-compose by your rational function, this is also a PV extension with Galois group GM. As long as your Galois group is connected, if you pre-compose by a rational function which is non-constant, okay, you don't change the Galois group. Okay, so if I set, let's say, to simplify a bit the notation, yi, which is e to the power fi of x, okay, then when I look at c of x, ki, c of x, yi, these are all Galois extension with Galois group GM. Do all have? Okay. And so if I look at C, so if I look at C of x and I adjoint all of them, this is the same thing as taking the composite of all these fields. Okay. But now this is the usual lemma this is the analog of the usual lemma of Galois theory. If you take a composite of field, the Galois group will be a subgroup of the product of the Galois groups. So this field is a PV extension. Okay. And if I take an element of the Galois group of this PV extension of C of x, and if I take an element of this Galois group, okay, sigma is an automorphism, then sigma of yi is equal to ci of sigma times yi for some constant ci of sigma. Okay, if I take the image by this Galois group of the solution of an equation, then the image will be a solution of the same equation. Okay, but these equations have solutions which are one-dimensional C vector space. And so the image of yi will be a constant times yi. Okay. And the morphism goes from this Galois group over C of x to gm to the power n, r, which to sigma associates C1 of sigma, CR of sigma. This identifies this group as an algebraic subgroup of gm to the power r. Okay. But now you can use this lemma. So of course, it's a case which is very easy because you're just trying to describe all the subgroup of gm to the power n. And the subgroup of gm to the power r, so conclusion is that the image is contained in a subgroup of the form product of the xi to the power ei is equal to 1 for ei in Z. Okay, the surjective morphism from gm to gm, these are just taking to the power ei for some I, and so the image is contained in that. And so you just have to set C, which is the product of the xi to the power ei. Okay, and by definition, sigma of C is equal to C for all sigma in the Galois group. Okay. And so by Galois correspondence, C is in C of X. Okay, so it's not exactly C, it's C of X.
How do we know that the assumption that H in this case is not equal to the product?
This is because the dimension of this field is strictly less than R. The dimension of this field will be the dimension of the Galois group. And so the fact that H is proper is exactly the hypothesis that we use that tell us that there is an algebraic foliation. H is proper because of that.
I'm a little bit confused. So what happened to all kind of non-trivial Galois assumptions here? So non-trivial in the sense that they will have non-abelian Galois group?
So because I'm only looking at the exponential. Okay, so if the exponential itself has Galois group GM. And that's why we only look at GM to the power n. But in the exercise, you have an exercise about proving the same kind of continuous result, but for the solution of the Airy equation. The Airy equation has Galois group SL2. Okay, and if you start with the Airy equation, solution of the Airy equation, and you compose it with rational function, you will be in the other case of Gorsat's lemma where you have also non-algebraic. So here it's because we started with a very simple function, which is the exponential function. That's why everything is commutative, and here it's a particularly easy case. In the article of Kolchin, where he used that, this is called algebraic groups and algebraic dependence. He uses for doing it for Bessel functions. Okay, so Bessel functions which have Galois group SL2. Okay. And so you get C of X here, but actually you will get that a rational function whose exponential is also a rational function is actually in C. And so that's how you get from C of X to C. Okay, so this is the classical case. I wanted to do a bit more, but I was a bit too slow. And I will do the case of principal connection tomorrow, and what replaces the Galois correspondence in this case. Okay. Nice. Okay.
Any questions? Okay, so if there are no questions, let me, well, first off, let's thank Remi again. And just like a couple of announcements. So now we go to lunch, and there are a few options. There is a cafeteria, there are some food trucks, and you're invited to follow one of us locals. And then in the afternoon, there is only one talk by George at 4:30, but the plan is to be back here around 1:30 so that we can chat math. And if you haven't picked one yet, out on the desk or the name tags where there are some exercise sheets prepared by Tal and Remi. And well, if you're not, if you're new to the topic, you're invited to approach those and then to informally approach them to ask questions that are, they're expecting you to ask me questions. So it's like, well, fine. And I would say that's about it. Okay. And you can stop the recording.
Stop.